Okay, this is lecture number 7. Okay, and in the past few classes we were looking at hold-in range, lock-in range and pull-in range of our PLL, where we use the only difference in the different kinds of PLL which we have used so far is in the loop filter f of s, and this is where we analyzed in the previous classes that why we need a different kind of f of s transfer function. So we have this phase error detector, the input V in, the output V out. Okay, and we considered two different transfer functions. One was f of s is equals to 1 plus s by omega p. Okay, and the other transfer function which we considered was this was tau p over tau I plus 1 over tau I s, where we use the pure integrator in the past. Okay, so now we have looked at why we need this is, let me just write here, these are two different cases, case 1 and case 2. Okay, so whether these are the only two different kinds of loop filters you will use in your PLL, or you need some other different kind of loop filter, that depends on actually the requirements of the PLL. Okay, now let me come to a little bit of a convention which is used in the PLL. The convention to define this loop filter is normally called as type and order. Okay, most of the PLLs are categorized as type 1 order 1, type 1 order 2, type 2 order 3 and so on. Okay, so what it is? Type is number of integrators in loop, and this is for, when I say number of integrators in the loop, this is for an open loop. So if you consider an open loop gain, we'll look for what is open loop gain of the PLL, so which is LG, which is equals to my phase error detector gain KPD into loop filter f of s into VCO transfer function 2 pi k VCO over s. So this is the open loop gain of the PLL. Now we will define how many the type will be defined as number of integrators. So what is the minimum number of integrators in this PLL loop? So any PLL is type 1 to begin with. Okay, the order is number of poles. Okay, so for this particular, for the case 1 fs, what is type and order? Let me just say type is 1 because there is only one integrator, which is 2 pi k VC over s. And what is the order? Order is 2. One pole is at 0, other pole is at omega p. So this is type 1 order 2. What is the second case? Type 2 and order. How many poles are there? 2 poles. So type 2 order 2. Okay, similarly you can have type 2 order 3 and maybe even type 3 and order 4 or so on. But the only thing which you can make sure here is that the order will always be greater than equal to the type of the PLL. Okay, so this is conventional. This is a convention to define a PLL by its type and order. Nothing more than that. Okay, now we have looked at, let me just remind you that we looked at different kinds of frequency tracking ranges, pull-in range. First one, let me just write this as frequency range acquisition ranges. This is just for a recap. Okay, we have lock-in range, pull-in range, and hold-in range. Okay, So I defined all these three ranges, frequency ranges for the PLL in the few previous classes. And lock-in range is a range where you lock to the PLL without any cycle slipping. That means without any phase error going more than 2 pi. Pull-in range is you lock to there's a frequency error with cycle slipping. And hold-in ranges that I define in very elaborate manner that how you can keep on giving a small step and see whether the PLL locks in, or you can give a large step with initial conditions and you see whether the PLL holds lock at that particular point. And I have also clearly specified that giving an initial condition is different from giving an offset to the PLL. These are two different things. Okay, so let me show you a few of the simulation that how these voltages or the ranges appear. So let me okay, so this particular figure is for an average phase error detector output. Okay, so we know that this is for a type 1 and order 2 PLL. Okay, let me just type 1 and order 2 PLL. Okay, and here I have shown average phase error detector output on the y-axis, and on the x-axis is the frequency error. Okay, so the example which I chose was KVCO was 100 megahertz per volt. Okay, and I am using a sinusoidal phase error detector. Right, and we figured out that for this the free lock-in range is actually 50 megahertz. Fine. So for a 50 megahertz plus minus frequency error between the input and the output. So let me just again tell you that I have this PLL block. I have the input signal and output signal. This is V in and V out. My F in initially is equals to 1 gigahertz. Okay. F out is also equals to 1 gigahertz, and I gave a delta F in of 1 megahertz, 2 megahertz. If I keep on changing my delta F in by 50 megahertz, my F out will also keep on changing. Okay, F out is going to track my F in, both plus minus 50 megahertz. And this with respect to KPD, KVCO, we can figure it out that this is 50 megahertz range, lock-in range. Okay. And this is type 1, order 1, order 2 PLL. Now, what happens as we cross the 50 megahertz? And this is where I told that with a type 1 PLL, you will not be able to lock in. Okay, but there will be some DC voltage. Means if you remember, means if I look at a V for a sinusoidal mixer output, even when this is not locked, the waveforms at V error was something asymmetric. As this is a beat, asymmetric beat frequency you will have, which is going to have certain DC values. So these are the different DC values which you have. And when we use a type 2 PLL, we actually amplify these DC values to a large enough value such that I get the required control voltage to lock at a desired frequency. And this is how we kept on increasing the frequency at the output. So we keep on changing the input frequency, the output frequency will keep on increasing. Okay, so we see, okay, we keep on increasing the input frequency to see if my output frequency increases. So let me tell you, it will hit your pull-in limit. So what is going to happen at pull-in limit? Let me show you two plots with respect to this. So actually for this particular PLL, now you know that the lock-in range and the pull-in range or the hold-in range for a type 1 PLL remains the same. Is there any confusion? So let me come back to this. So for a type 1 and order 2 PLL, right, you do not have any integrator, so you cannot amplify any DC value. So your lock-in range, pull-in range and hold-in range are all the same, because they are all coming with, there's another expression we had, delta omega divided by KPD, KVCO this should be less than equal to 1, because this it has a steady state phase error, sign of phase error, right? So here the lock-in, pull-in and hold-in are same. Only when we introduce an integrator in the loop with a sinusoidal phase error detector, that time the pull-in range increases. Okay, so this is for, if you have any confusion, please ask, don't make any assumption right now. So this is for type 2 and order 2 PLL. Okay, so you see that there is existing an asymmetric beat node which you are having, which has a certain DC value. So on the x-axis, on the first plot, you see the phase error. On the y-axis phase error, and here the phase, this is V error, which is actually equals to, V error is equals to half of sine of phase error. Okay, this is where someone asked the question that you see that the phase error means the plot which the y-axis which you are looking here is going from 0 to minus 300 times 3000 times 2 pi. So you are repeatedly crossing 2 pi range. Okay, and when you are repeatedly crossing 2 pi range, you see the V error that is going from minus 0.5 to plus 0.5. But how fast it is changing, this is plotted on a logarithmic plot, but you will see that this is an asymmetric waveform which has certain DC value which keeps on amplifying, which keeps on like accumulating to get a certain DC value in the end. Okay, so I have chosen two cases. In one case, delta F is equals to 2.25 gigahertz. Okay, and in another case, delta F is equals to 2.3 gigahertz. Okay, and why I chose 2.25 and 2.3? Because this is another expression which I told last time, that the pull-in limit for this particular type 2 order 2 PLL is less than equals to k times under root of 2k dc by k minus 1. For a sinusoidal phase error detector with an integrator and the proportional path, this is the limit pull-in limit. Okay, now so this 2.25 gigahertz is actually at that limit only. And whatever you calculate with this equation may not be exactly, it will be near about here on the value. Okay, so now you see the difference. In one case, you see that this particular phase error means it does all the such kinds of thing till the time it gets the DC value and it saturates. But if the frequency is beyond the pull-in limit, okay, then it just keeps on ringing and this phase error keeps on increasing. It does not acquire that required V control voltage. Means it's like it does not have a steady state phase error, so it will not have a steady state V error, so it is not going to have a steady state control voltage. It will keep on changing. Okay, but if I give any initial condition to the PLL, yes. Yeah, just a minute. Yeah, tell me. Phase error is? No, phase error is, so the thing is, you gave the input frequency as an higher frequency, right? And you see that you start your oscillator from the nominal, so this simulation is for, I gave my Fn as, so I told you, Fin initially is equals to 1 gigahertz, F out initially of free running frequency is equals to 1 gigahertz. Okay, and I gave a delta F of 2.25 gigahertz at time instant t equals to 0. So input frequency is higher than the output frequency. Then you see that means if you just look at the phase error normally, you will have what? Phi error of t means if there is no feedback in the loop, that will be omega in minus omega out, and it depends on the sign and every other thing, right? So whether it is increasing or going in one direction, it should achieve that final steady state frequency. Okay. Okay, it does not have to do anything else. And this plot is while considering the feedback loop, so it is not increasing with a continuous rate, like same slope. And one other thing which you should realize, this is on a logarithmic plot, so you will not see a linear scale at all. Okay. Initially it's 0 because I start at time, it means both the sine waves are starting at same time instant t equals to 0. So if you calculate at that particular value, it will be 0. This is like the initial condition. You can take anything. Yes. Okay, so why is it not? I think this is a question which is repeated again. Why this steady state value in type 2 PLL is not? Can someone tell me? So let me ask you this. What is the pull-in limit of an ideal type 2 PLL? When I told you that okay, this is not infinite, what's the problem? DC gain is not infinity. There is some finite, means when I am trying to implement it, the DC gain is not infinity, it is actually high. Okay, so when I write this as type 2 PLL here, it is like when I am trying to implement it, the amplifier or whichever way I am trying to implement this integrator, that gain is limited. Okay, ideally it should go to infinity, you are right. So ideally this error voltage should be 0. Okay, so if I give any initial condition to my PLL, let me, okay, this is, so let's look at the control. Okay. Huh? What ideal condition? No, if I would have showed you ideal condition, then the hold-in and pull-in are both sitting at infinity, right? Then I would not be able to show you that how the pull-in is different from the hold-in. Okay, that's the only thing. Okay, so now in this particular case, you see this is here I plot a control voltage with respect to time at which for the simulation. So there are 3 plots. One is delta F 2.25 gigahertz without any initial condition. And I am telling you 2.25 gigahertz delta F is lying within the pull-in limit. So no matter what it does for some time, at the end it should settle. Okay. Then I gave a 2.3 gigahertz of delta F without any initial condition. And this point is beyond the pull-in limit. So no matter how long do you run the simulation for, it is not going to settle. Okay, and then next one is 2.3 gigahertz delta F, but with initial condition. It can have initial variation, but finally it should be settled. Okay, so you see the 3 conditions. In one case, this is the one with initial condition within pull-in limit. This is beyond the pull-in limit, no initial condition, and if I give initial condition for large frequency, it actually remains stable there. No problem. Okay, there will be, means I give an image, this is like a very large scale, so if I give a exact condition which I want in the steady state, but there will be some amount of, some fluctuation that depending on some initial offset or something, it will finally settle. Yes. 2.3 gigahertz is inside the hold-in range. Okay. So I told you, this is for, again, a recap. So I told that, let us say if this is delta F which I am plotting, and I have this delta omega pull-in. So after the delta omega pull-in, either I can give like very, very small omega, delta omega 0, I can keep on increasing on this frequency range. Right? Or the second, another simulation which I told, with delta omega equals to 0 at this point, I will give directly a step of delta omega greater than delta omega p with the initial condition. So it's like whether I am, let us say here, and I just take a small delta step on the right beyond the pull-in range is equal to that I give a delta omega step but with all the initial conditions. This is one of the same simulation or the condition for the PLL to operate. Okay. So now you see that, but there might be some small change here, but it will settle out pretty fast. Oh, so I do not know if you can realize that there is some small glitch in the beginning. Okay. Now what happens, I can give all these delta omega and I can give the initial conditions, but what happens when we reach the hold-in range? So let me show you another plot. Okay, so for this particular case, it is my delta f of h is close to 5.5 gigahertz. Okay, for this PLL. So you see that 5.498 it is log, 5.499 it is log, but 5.5 no matter, means I started with the same initial condition. Right? This is also to tell you, you can start with the initial condition, and if you only run for a small time, you say it is log, means you should run for a large time to see whether it remains in log or not. Right? After some phase error change, this just blows up, and then it's keep on continuing. Okay. Don't think this is going to come back and settle like this. That is not going to happen. If that could happen, it would be it could have done the same in during the pull-in time. Yes.
So, if you are the last, which is taking it outside, taking the hold-in range, then give it by the initial condition force. So, select the PLLs or the log PLL.
Go again.
Like, we give one fixed step. So that changes the PLL to the hold-in range.
Yes.
And we have select the initial condition force.
Yes.
So, this spread curve shows that initially stays in the log state, then it goes forward.
Means initially the state variable. So let me just one example I will tell you. I think so. Let us say for the PLL which we for the phase error mix detector which we are using, right? We know that the output of the phase error detector at max can be what value? Half, plus minus half, right? And now I am using an integrator which has some finite DC gain. It is not infinity. Finite DC gain, let us say that is even equals to 10 power 4. So high. Right? That means the voltage here at the best can be 10 power 0.5 times 10 power 4 plus minus. Okay? And then it has certain VCO, KVCO range, and let us say the VCO range is 1 megahertz per volt, for example. Right? If this is 1 megahertz per volt and that multiply with the maximum input available at the control voltage, how much this is equals to, for example, 5 gigahertz. Mag into 5 is a 5 gigahertz. Right? So now, if I say for 5.5 gigahertz, I want to log, which is beyond the hold-in range actually. Right? So for this 5.5 gigahertz, I need an initial condition here, which is 0.55 times 10 power 4. Agreed? Now I gave that initial condition. As I was giving before, there is no problem in the control voltage, can take as much as I can give. I gave that condition. But for that 0.55, can I have any error, any steady state error at the input, which can give me 0.55? Means this gain is fixed, I can't change this gain, this error is fixed. So no matter, even if you give this initial steady state, first thing is that steady state variable does not exist for all the state variables, right? Even if you try to enforce one, and when the loop runs, it will find that that is not a stable point. But if I start with 0.5 into 10 power 4, I gave the initial condition as even as half, right, all the variables, it will remain there. Do you get that? So all these means, if you change this phase error detector from sinusoidal phase error detector to some other phase error detector, the holding range will change. So this is for a particular type of PLL and a particular type of the blocks which you are using. Okay. Any question with this? So do you think that it is not that difficult to run all these simulation and find these problems? I think it's easy, right? You have to just write the difference equations. Let me just put it that way. Okay. Any questions regarding these ranges or anything when we move on?
So by getting the initial condition, the simulation you can avoid this problem.
No, but you mean by giving the initial condition you can, what problem are we talking about? Right?
Then we can do that.
No, I am saying you cannot even then do that. Because 0.55 is not a steady state value at all. Means you just said, okay, I have delta F this much large, so I can give this value. Okay, let me put it. But the loop will not be stable at that point, because to have 0.55 here with this much of DC gain, you need to have a larger value at the output of phase error detector. And the phase error detector's characteristic property is it cannot have a value more than 0.5. So for any given PLL, if someone asks you what is the maximum delta F you can have, without even going into much, just look at the DC values. You do not know how you are going to generate this value. That doesn't matter. It's like if I have these variables, it will remain locked at that point, because that's a stable condition. Yeah, one by one, yeah. You think that this is stable? No, so let me ask you that the y-axis is a current control voltage, and if this control voltage is changing all the time, means you see a red patch, right? This is actually all changing. Means the difference with this is just a single line and this is a big patch, right? Means for example this one, it is oscillating all the time. Yes, what's your question? No, so whatever you do, you will do for one time only, right? You design a PLL with a certain amplifier gain, no matter in place of 10 power 4, you can have 10 power 9, for example. Doesn't matter. There is a limit. There is a numerical limit to it. Okay. It's just not infinity. Can we find the? No. It's finding the pull-in range is no. I think the pull-in range, it does not come that easily. So there is one. Okay, I didn't want to go into maths. So the thing is, if you see that after this 50 megahertz, right? I told you there is this asymmetric beat node which you will have, right? Which will have a certain DC value. This is this DC value. That loop filter which you are using, that loop filter is amplifying the DC value. And this is happening it's not like multiplying with the DC gain, it is happening all continuously, right? So you use these voltages, first you have this asymmetric node, then you use these voltages, then you write the loop filter, how the loop filter is operating on it, and then you find that if that has a solution or not in equations. Okay, and that solution gives you actually a pull-in limit of this kind. So it is not easy to get the pull-in limit with more of a hand waving. If you know what? Yeah, that you can do. That you can do. But let me, okay, this is one interesting thing. So let us say whether I give 1 delta omega 1, I use 2 frequencies. This is beyond the, sorry, 1 delta omega 1 is beyond the pull-in range, and delta omega 2 is within pull-in range, for example. Okay, these are the 2 frequency things, 2 frequency variation. Now, surely I can use the DC gain of the loop filter, the KVCO of the oscillator, to find what will be the steady state phase error, steady state steady state control voltage, and steady state V error, phase error, V error, and control voltage by using the DC values. That you can do, but that does not tell you whether this is within the pull-in range or outside the pull-in range. Okay, and it's not that, okay, only for the frequencies which are beyond the pull-in range I should give initial conditions and check whether they are locked or not, right? Even if you give the initial conditions for the frequency errors within the pull-in range, it will remain locked there. Okay, you can give me, there is no, nothing like only for frequencies beyond the pull-in range you can give the initial state and to verify it is locked. You can give for any frequency error. Okay, and let me, means this is like in a large scale, let me tell you in a small scale also. So okay, we have this loop gain defined as KPD, f of s, and 2 pi KVCO over s. Okay, so I have to plot this, draw this PLL. So I have PD, fs, and KVCO. Oh, sorry, let me just write this as, make this as VCO itself. Okay, so I have now, I will consider input phase, output phase, this is V error, this is V control voltage. Okay, now I gave some kind of steady state, means I gave some kind of initial frequency error or phase error, and finally the PLL locks. Okay, it is within the, you can say, hold in range or pull in range, whatever it is, right? I want to know what is the VE, VC, and for that matter even phase error at the input. So what do I want to know? I want to know limit of t tends to infinity, phase error of t, limit t tends to infinity, V error of t, and t tends to infinity, even V control of t. I want to know. The only thing which I am telling you is that whatever the frequency error or phase error we give at time instant t equals to 0, finally the PLL locks. If the PLL locks, it will reach a certain steady state. Okay, how will I find all these values? Means surely you can do all kinds of adopt different techniques, but don't you think that once the PLL locks, everything becomes a small signal, isn't it? So for any frequency step I can do limit t tends to infinity is equals to s tends to 0 into s of phi error of s, and so on. Okay, now let me again, this is loop gain. We know that phi out of s is equals phi out by phi in of s is equals to loop gain by 1 plus loop gain. Okay, and even phi out of s by, let us say, omega in of s is equals to 1 over s times loop gain by 1 plus loop gain. So you can use all these transfer functions to find the final steady state values. Means the one which I just found without even doing any of these things, by just saying, okay, this is the DC gain of this value, this is the DC gain of this particular transfer function, so it will, the final value is this. So when I am doing this s tends to 0, actually I am finding the DC value itself, isn't it? Okay. Now, another thing is, means I think everyone can find all these values no matter what, means this is just given the transfer function, you can just substitute the values and see whether any value exists or not. Okay, from here you will also find that if some value for a given kind of a frequency or phase change or given kind of a PLL type 1 or type 2, you will, if any of these steady state values is infinity, right, that means the PLL is not locked. If any of these steady state values is beyond the range of the block, like the phase error detector, if somehow means I do all these things, I gave a frequency error and I found that this phase error means it gives me a value, for example, it gives me 0.6, just an example. So don't say that, okay, this 0.6 is the value I am getting with all this steady state operation and the PLL is locked. No, this value is just not infinity, but this value is beyond the range of the actual sinusoidal phase error detector. So if any value is beyond that range, it's not possible. Okay. Similarly, means we have so far we said that VC can take any values, but there will be limit on the VC itself. It can go, let us say, plus minus 10 volt only. You are getting a VC of 11 volt. That means it will not. Okay. So you have to cross check with the actual limits of the block, whatever you are finding. Okay. So now, means this is, so we have a PLL, we start with some initial frequency, phase error, and finally the PLL logs, everything is really good. Okay. So then when everything becomes really good, then we start the small signal analysis of these blocks. Okay. And this is, mean we will deal with this in much more detail, but this is just for information here that the phase error detector will, whichever point a phase error it logs to, for that particular phase error, it will have a certain phase error detector gain. Okay. And how will I get that gain? So let me tell you one by one. So I have this one as f of s and VCO with a gain of 2 pi k VCO over s. Okay. And so once the PLL is locked, and let us say the locking condition is phase error is equal to, for example, something as pi by 3, just for an example. Okay. For this pi by 3, the V error is equals to sine of pi by 3, which is how much? I forgot this value. This is root 3 by 2, right? Sine 60 degrees into half. Okay. For this, there will be some filter loop filter output value also. So f of s, I will calculate this value in lock condition. This will be means depend on the DC gain. It is also going to have some value. Right, so PLL is locked, and VCO is also means if I look at V out will be equals to sine or cosine whatever it is into 2 pi k VCO times f free running frequency times t plus 2 pi k VCO into whatever V control voltage I am going to have. V control plus VE here, V dt. This is my actual PLL. What? Okay, fine. Yes. Right? So this is my lock condition. Now, if I give a small, now the PLL analysis means once it's a lock condition, this is equal to your, you can say, an amplifier. Means this is, I will just tell you, this is like an amplifier where you give the common mode input potential VCM at both the inputs nodes, and you have a VCM, let me call this a VCM in, VCM out. Okay, this is what you have. It can have some gain with respect to frequency. right? Here A can be equals to A naught by 1 plus S by omega P. This is an amplifier. What is VCM voltage? It can be 0.1, 0.2, anything. Similarly, what is this phase error? It can be anything. Okay, but within the limit. Now, if I have to define this A naught gain of the amplifier, what do? I actually find that what is the gain of the input pair of the amplifier at this given common mode voltage. Similarly, I will define the gain of the phase error detector at that particular phase error at which it is locked. Right? So, if you are using a sinusoidal phase error detector, which has, means this is just for an example, the output of the phase error detector V error with respect to phase error is this. This is what we know, right? And if I am locked to a condition of phase error of pi by 3, then the gain of the phase error detector should be defined at this point, not anywhere else in the loop. Huh? Yeah, at around this point only you are going to apply a small signal. Don't apply small signal with the anywhere else, right? So now here in the case of amplifier, we give input VIP and VIN, right? This is what we give, and then we found that okay, ideally this should be equals to V out is, now this V out is equal to A times VIP minus VIN. Okay. Similarly, the same kind of analysis will happen in case of the PLL also. It's locked, everything is fine. Now I give a small input phi of input. Okay. Now for some reason, some people write this as delta phi in, which is a small phase error change at the operating point. Okay. So now this delta phi in, and let me just come back here. So for the given phase error, phase at the input, V error is equals to KPD, which is defined at the phase steady state phase error times delta phi in. Okay. Now don't come and say that this V error is equal, means you can very well, the absolute V error, if I look, let me just make a difference between large and small scale. Absolute V error is equals to V error steady state plus KPD times delta phi in. Okay. But when I am considering a steady state, I am considering only the small signal picture. I am not going to write for this. I am only going to write, I am only going to analyze for the disturbances or the small changes in the system. So all the steady state points I am going to remove from my equations. Okay. So now for this particular V, I have phase error, I have VE. Then for given VE, I will have whatever the loop filter, F of S times VE. All these are small signal, right? Now omega out is equals to 2 pi, sorry, omega out is omega out is equals to KVCO times VC, and phi out is equals to 2 pi, just a minute, yeah, 2 pi omega out over S. So all the equations on the left which you are seeing, all these equations are for small signal changes in the PLL. Okay. There, and it means you took the, you ran the PLL in a steady state, you find all the operating points, and then you start analyzing it for the small changes. Yes.
PLL is small.
Yeah.
Maybe this is small value around that, so that how small signal will be valid.
Yes.
But suppose if my PLL is locked, at some point will the small signal will be gone if I large. Okay. After that, as you said last time that if we use small frequency steps, the operating point will change.
Yes.
Operating point will change. But in that case, we have to now clear the.
No, so the thing is, let us say this is specifically for the holding which I think you are referring to. So here, if I move from one operating point to another operating point, yes, your small signal gains change, can change. Okay, but the kind of analysis which we will do in this case, even your small signal approximations will remain valid. We are not considering for large changes here. Okay, and for noise, thermal noise or whatever the noise is coming, the noise should not be so large that the PLL doesn't lock at all, means kind of that. So this analysis is most of the time it is used for the noise, or it is used for modulating this PLL with a very small signals. Okay. This is not like, okay, you give the frequency change by a large amount and you think that the PLL is going to go by these laws or these equations. It will not. Don't even think that it is going to work that way.
If I want to log to some other frequency around this small signal for this small signal will be valid around this 500.
Yes, yes.
If I want to log at some other, I have to log again and I have to change it.
No, the question is whether you have to lock again. What does that mean? So let me just say that, for example, if do I have any example here? Okay. So let us say when I give an initial frequency step, I give an initial frequency step and my V control voltage does this and finally it locks, right? I give another frequency step at the top of it, right? So I give another frequency step after it is locked, it may do like this, right? It does not mean that if you want to see this final frequency step from here, or if I give the same frequency step, this last frequency step, which may be, it may lock, both may lock to the same thing, but the dynamics of both will be different, right? And then it reaches steady state. So coming back to your question, that if I am locked to a certain point and I give some delta omega at this point, don't think that this delta omega is the same as from initial delta omega. No, your operating point has changed, so you should start from there. Okay. So one thing, make sure that please do not apply this small signal analysis for your large scale changes. Okay, and sometimes we write all this as delta, everywhere we write as delta, and because we can't write all the delta, means this is too much of work for us, so we remove delta all the time, okay, and we say, okay, this is phi in. So please be sure what convention do you use in your PLL. If you are doing a small signal analysis, be sure that the phase which you are referring is a small signal only. Okay, let me stop here.